Tonight, we're going to explore something that sounds like science fiction, but is actually one of the most brutal realities in all of physics. Deep space. The region beyond our planet's protective bubble. You've seen movies about astronauts floating through space, heroes venturing between stars, colonies on distant worlds. But here's what those movies don't show you. Deep space exposure involves something most people completely misunderstand. And by the end of tonight, you're going to see why the universe beyond our planet isn't just dangerous. It's hostile in ways that attack every system your body depends on. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with something you already understand: survival. You know what it takes to survive in your everyday environment. You need air to breathe, water to drink, food to eat, a relatively stable temperature, protection from the elements. These are basic requirements that your body has evolved to expect. Earth provides all of these things automatically. The atmosphere contains oxygen at the right concentration, roughly 21%. The temperature stays within a range that allows liquid water to exist. Gravity holds everything in place. The magnetic field deflects harmful radiation. The ozone layer blocks deadly ultraviolet light. All of this happens without you doing anything. It's the baseline, the default state of existence that your biology assumes will continue. Now, imagine removing each of these protections one by one. That's what deep space does. It strips away every single thing your body needs to survive, all at once, instantly. Deep space isn't just empty. It's actively hostile in ways that are hard to overstate. Let's start with the most immediate problem: pressure, or more accurately, the complete lack of it. Right now, sitting wherever you are, you're experiencing atmospheric pressure. About 14.7 pounds per square inch, or 101,000 pascals. That's the weight of the entire column of air above you, pressing down. It doesn't feel like anything, because it's pressing equally from all directions. Your body has evolved to operate under this pressure. Think about what that means for a moment. Every square inch of your body is experiencing nearly 15 pounds of pressure. Your entire body surface area, roughly 20 square feet for an average adult, is under about 43,000 pounds of total force. That's over 20 tons of pressure. You don't feel it crushing you because there's equal pressure inside your body pushing back out. Your blood, your tissues, the air in your lungs, all of it is at the same pressure as the atmosphere around you. It's balanced. Equilibrium. This equilibrium is so fundamental to how your body works that most biological processes depend on it. Your cardiovascular system pumps blood through vessels at pressures carefully regulated relative to atmospheric pressure. Your respiratory system depends on pressure gradients to move air in and out of your lungs. Even your cells maintain osmotic pressure balances that assume external atmospheric pressure. The human body is a machine calibrated to work at 1 atmosphere of pressure. Take that away, and the machine breaks down catastrophically. Your lungs work because of pressure differences. When you inhale, your diaphragm expands your chest cavity, creating lower pressure inside your lungs than outside. Air rushes in to equalize the pressure. When you exhale, you compress your chest, creating higher pressure inside than out, and air rushes out. This entire process depends on having atmospheric pressure as a baseline. Your blood, your bodily fluids, the gases dissolved in your tissues, All of these exist in equilibrium with atmospheric pressure. Now picture what happens when that pressure disappears. Instantly, completely. This is what's called exposure to vacuum, and the effects begin in less than 1 second. The first thing that happens is ebulism. That's the formation of gas bubbles in bodily fluids. Here's how it works. At normal atmospheric pressure, gases like oxygen, nitrogen, and carbon dioxide remain dissolved in your blood and other fluids. The pressure keeps them in solution, the same way a closed bottle of soda keeps carbon dioxide dissolved in the liquid. Think about what happens when you open a soda bottle. That hissing sound is carbon dioxide coming out of solution, the bubbles that form and rise to the surface. That happens because you've reduced the pressure by removing the cap. Inside your body, you have gases dissolved in all your fluids. Nitrogen makes up about 78% of the air you breathe, and it dissolves in your blood and tissues. Oxygen dissolves too, though most of it is carried by hemoglobin in red blood cells. Carbon dioxide, the waste product of metabolism, is dissolved in your blood as it's transported to your lungs. All of these gases are in equilibrium with atmospheric pressure. When you suddenly remove that pressure, just like opening a bottle of soda, those gases come out of solution. They form bubbles everywhere. But unlike a bottle of soda where bubbles just rise harmlessly to the top, in your body, these bubbles form inside your circulatory system, inside your tissues, inside your organs. And they cause immediate, severe damage. But when you suddenly remove that pressure, just like opening a bottle of soda, those gases come out of solution. They form bubbles everywhere, in your blood, in your saliva, in the fluid around your eyes, in your tissues. The medical term for this is decompression sickness, though you might know it as the bends. Scuba divers can experience a mild version if they surface too quickly from deep water. But what happens in the vacuum of space is incomparably more severe. It's not a gradual pressure change from a few atmospheres to one. It's an instantaneous drop from 1 atmosphere to essentially 0. The bubbles form everywhere at once. Your blood begins to foam. Your tissues swell as gas expands within them. The water in your mouth, your throat, your lungs begins to boil. Not from heat, but from the lack of pressure. This is vapor pressure boiling. Water normally boils at 212 degrees Fahrenheit or 100 degrees Celsius at sea level pressure. But the boiling point of water depends on pressure. At lower pressures, water boils at lower temperatures. At the top of Mount Everest, where pressure is about 1/3 of sea level, water boils at about 154 degrees Fahrenheit or 68 degrees Celsius. In the near vacuum of space, water boils at body temperature, 98.6 degrees Fahrenheit or 37 degrees Celsius. Your saliva boils on your tongue. The moisture on your eyes boils away. The fluid in your lungs begins to bubble and froth. This sounds like something from a horror movie, but it's pure physics. It's what happens to any liquid in a vacuum, and the physics behind it is well understood. The boiling point of a substance depends on the vapor pressure needed for molecules to escape the liquid state. At higher external pressures, molecules need more energy, more kinetic motion, higher temperature to overcome that pressure and escape. At lower external pressures, less energy is needed. In a perfect vacuum, essentially no external pressure, molecules can escape the liquid state at any temperature above absolute 0. Your body temperature is 98.6 degrees Fahrenheit, or 37 degrees Celsius. That's far above absolute 0. more than enough for water molecules to escape into vapor in a vacuum. So the moisture in your mouth, your throat, your lungs, the surface of your eyes, all of it starts boiling, not violently like water on a stove, more like a rapid evaporation, flash boiling into vapor that immediately disperses into space. This has been observed in experiments. Not with living subjects, obviously, but water exposed to vacuum chambers behaves exactly this way, instant boiling at room temperature. The same physics applies to the fluids in your body. Now, here's something most people don't realize about space. When we talk about the vacuum of space, we're talking about different levels of vacuum depending on where you are. Space isn't completely empty. Even in interstellar space, far from any star or planet, there are about a few atoms per cubic centimeter. That might sound like nothing, and compared to Earth's atmosphere, which has about 10 to the 19th molecules per cubic centimeter, it is effectively nothing. But it's not absolute zero pressure. It's just so close to zero that the difference doesn't matter for our purposes. Near Earth, in low orbit where the International Space Station flies, there's slightly more matter. The outer reaches of Earth's atmosphere extend hundreds of miles up, getting thinner and thinner. At the ISS altitude, about 250 miles up, there are still enough air molecules to cause drag on the station. Not much, but enough that the station gradually loses altitude and needs periodic boosts to maintain its orbit. This is called orbital decay. Without those periodic boosts, the ISS would eventually spiral down and burn up in the atmosphere. But even at that altitude, the atmospheric pressure is about 1/1,000,000,000th of sea level pressure. For human purposes, it's vacuum. Exposure to it would have all the same effects we've been discussing. Further out, beyond Earth's atmosphere entirely, the density drops even more. In deep space, far from planets and stars, you might find 1 atom per cubic centimeter, maybe less. That's as close to perfect vacuum as you can get in nature. And that's the environment humans would face on a journey between planets or between stars. Pure, nearly perfect vacuum. No pressure, no protection. Nothing between you and the cosmic radiation streaming through space. At the same time, the gas in your lungs expands. Your lungs at normal pressure contain about 6 liters of air. In a vacuum, that air tries to expand to fill infinite space. If you're holding your breath when exposed to vacuum, your lungs rupture almost immediately. The expanding air tears the delicate tissue. This is why scuba diving instructors teach you never to hold your breath when ascending. Even the pressure change from 10 meters underwater to the surface, about 1 atmosphere of difference, can rupture lungs if you hold your breath. Going from 1 atmosphere to 0 is far worse. But here's the thing. Even if you don't hold your breath, even if you exhale as quickly as possible when exposed to vacuum, you still only buy yourself a few more seconds. Because the damage from embolism is already starting. And that's just the beginning. Let's talk about oxygen deprivation. Your brain consumes about 20% of your body's oxygen, despite being only 2% of your body weight. It's an energy-hungry organ, constantly processing information, maintaining consciousness, keeping your body's systems running. Without oxygen, brain cells start dying within seconds. In a normal environment, if you hold your breath, you have maybe a minute before you pass out. Maybe 2, if you're trained. But that's with your blood still carrying oxygen, with residual air in your lungs. In vacuum, you have no air in your lungs. It's been forced out by the expanding gases, or it's escaped through your mouth and nose. Your blood is starting to foam from embolism, which means it can't carry oxygen effectively, even if there was any to carry. Consciousness fades within about 10 to 15 seconds. That's how long it takes for the oxygen already in your bloodstream to be consumed by your brain. After that, you're unconscious. Brain damage begins within minutes. Complete brain death within 4 to 6 minutes. But you won't last that long, because while your brain is shutting down from lack of oxygen, several other catastrophic processes are happening simultaneously. Remember those gas bubbles forming in your blood? They're causing circulatory problems. Massive ones. Your heart is trying to pump blood through your arteries and veins, but now that blood is full of bubbles, gas bubbles can create blockages, preventing blood from flowing properly. This causes areas of tissue to be starved of oxygen and nutrients even faster than they would be from simple lack of air. Your heart might even start pumping foam instead of liquid blood. At this point, even if you were somehow rescued and repressurized within seconds, the damage would be catastrophic. The bubble formation, the tissue damage, the oxygen deprivation, all of it compounds. People have survived very brief exposure to near-vacuum conditions in accidents. There are documented cases from the 1960s when spacesuit failures exposed astronauts to near vacuum for a few seconds. They survived because they were immediately repressurized. But they described feeling the saliva on their tongue boiling. They described feeling their skin swelling. They lost consciousness within seconds. And these were exposures of maybe 10 to 15 seconds at most. A longer exposure would be fatal. No question. But we're not done. Because pressure and oxygen are just the first problems. Let's talk about temperature. Space is cold. Everyone knows that. But what does cold mean in the context of space? Most people think of space as having a temperature of absolute zero, negative 459.67 degrees Fahrenheit, or negative 273.15 degrees Celsius, the coldest possible temperature where all molecular motion stops. That's not quite accurate. Space itself doesn't have a temperature in the conventional sense, because temperature is a measure of how fast molecules are moving. In a vacuum, there are so few molecules that the concept of temperature becomes complicated. What does exist is thermal radiation. Everything with a temperature above absolute zero emits electromagnetic radiation. The hotter something is, the more radiation it emits, and the shorter the wavelength. Very hot objects emit visible light. Cooler objects emit infrared radiation. Even very cold objects emit some radiation, though at very low intensities and very long wavelengths. The cosmic microwave background, the leftover radiation from the early universe, fills all of space and has a temperature of about negative 454.75 degrees Fahrenheit, or negative 270.42 degrees Celsius, just a few degrees above absolute zero. So if you were floating in deep space, far from any stars, you'd be surrounded by this faint microwave radiation at negative 270.42 degrees Celsius. That sounds lethally cold, and it is, eventually. But here's the counterintuitive part. You wouldn't freeze instantly. You wouldn't turn into a block of ice in seconds like you see in movies. The reason is that heat transfer in space works differently than it does on Earth. On Earth, you lose heat through three mechanisms: conduction, direct contact with something cooler; convection, heat carried away by moving air or water; radiation, emission of infrared light. In a vacuum, conduction and convection don't work because there's nothing to conduct heat to and nothing to carry it away. The only way you lose heat is through radiation. And radiation is a relatively slow process for something at body temperature. Your body at 98.6 degrees Fahrenheit or 37 degrees Celsius emits infrared radiation. In the absence of any external heat source, you'd slowly cool down as you radiate heat away. But it would take hours, not seconds. The immediate threats in space, the pressure problems, the oxygen deprivation, would end you long before freezing became a concern. That said, if you were somehow able to survive the vacuum exposure, if you had unlimited oxygen and perfect pressure protection, but no thermal insulation, you would eventually freeze. It would be a slow, gradual cooling. Your extremities would cool first, then your core. Eventually, your body temperature would drop low enough that metabolic processes shut down. Hypothermia, loss of consciousness, death. But again, this would take hours, not seconds. The movie image of someone freezing solid instantly in space is pure fiction. There's also the opposite problem: heat. If you're close to a star, anywhere in the inner solar system, for example, you're being bombarded with intense radiation. The sun pours out energy in all directions. Near Earth, the solar radiation delivers about 1,361 watts per square meter. That's called the solar constant. Half of your body might be facing the sun, absorbing this energy. The other half faces away into cold space, radiating heat away. Without an atmosphere to distribute heat, one side of you would heat up while the other side cools down. You'd experience extreme temperature differences across your body. The sunward side could reach temperatures above the boiling point of water. The shadow side could drop to well below freezing. This temperature gradient would be uncomfortable if you were conscious, but again, you wouldn't be conscious. The vacuum exposure would have ended you long before the temperature extremes became the main problem. So pressure and temperature are catastrophic threats, but there's more. Let's talk about radiation. Earth's atmosphere and magnetic field protect us from a constant barrage of radiation coming from space. This radiation comes in several forms. Solar radiation, the stuff coming directly from the sun; galactic cosmic rays, high-energy particles from outside our solar system; solar particle events, occasional bursts of charged particles from solar flares. Most of this radiation is blocked or deflected before it reaches the surface. The atmosphere absorbs a lot of it. The magnetic field deflects charged particles, channeling them toward the poles, where they create auroras instead of hitting the ground. We're protected without even realizing it. To understand just how much protection Earth provides, consider the different types of radiation and how they're stopped. Solar radiation includes the full electromagnetic spectrum: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Most of this passes through space without any problem. It's just electromagnetic radiation, photons traveling at light speed. The visible light obviously reaches us. That's what allows us to see, to have photosynthesis, to have solar panels. Infrared radiation, heat, reaches us too. That's part of how the sun warms the planet. But the high-energy end of the spectrum, ultraviolet, X-rays, and gamma rays, these are mostly blocked. The ozone layer in the upper atmosphere absorbs most UV radiation. What gets through, UVA and some UVB, is what causes sunburn and tanning. But the really damaging UVC is completely blocked. In space, there's no ozone layer. All that UV radiation hits directly. UV radiation damages DNA by causing chemical changes in the molecular structure. It can cause mutations in cells. Over time, it leads to skin cancer. A person exposed to the full UV spectrum in space would get severe burns on exposed skin within minutes. Not from heat, from radiation damage at the cellular level. The skin would redden, blister, and eventually develop lesions. This is separate from the other problems we've discussed. This is purely from UV exposure. Then there's X-rays and gamma rays from the sun. The sun produces these during solar flares and coronal mass ejections. They're high-energy photons that can penetrate matter. On Earth, they're absorbed by the atmosphere before reaching the ground. In space, they pass right through. A solar flare, producing intense X-ray and gamma radiation, would irradiate anyone in space who wasn't shielded. The radiation would penetrate tissue, damaging cells throughout the body. But solar radiation, as dangerous as it is, isn't even the worst threat. The real danger comes from galactic cosmic rays. These are atomic nuclei, atoms stripped of their electrons, accelerated to enormous energies. They come from outside our solar system, produced by supernova explosions, neutron stars, black holes, and other violent cosmic events. When a star explodes in a supernova, it releases energy equivalent to the sun's entire lifetime output in just a few seconds. That energy accelerates particles to speeds approaching the speed of light. These particles, mostly protons but also heavier nuclei, like helium, carbon, oxygen, iron, shoot out into space in all directions. They travel through the galaxy for millions of years. Eventually, some of them pass through our solar system. And when they hit Earth, most are deflected by the magnetic field or absorbed by the atmosphere. We're protected. In space, there's no protection. A galactic cosmic ray is a single atomic nucleus moving at perhaps 90% of light speed. It has kinetic energy millions of times higher than particles in the most powerful accelerators on Earth. When it hits human tissue, it doesn't just damage the cell it hits. It creates a cascade of secondary particles. It ionizes atoms along its path, ripping electrons away, creating a trail of chemical damage. It can shatter DNA molecules. It can destroy cellular machinery. A single cosmic ray hit can kill a cell outright or mutate it in ways that lead to cancer later. The energies involved are just enormous compared to biological scales. Now, one cosmic ray hit won't end you. You're exposed to some cosmic rays, even on Earth. They make it through despite the atmosphere. You're constantly being hit by particles. Most pass through harmlessly. Some hit cells and cause damage. Your body repairs most of that damage. That's what DNA repair mechanisms do. But the dose makes the poison. On Earth, you're hit by maybe a few cosmic rays per square centimeter per second. Most don't cause lasting damage. Your risk of cosmic ray-induced cancer from a lifetime of Earth exposure is tiny. In space, the flux is much higher. hundreds or thousands of cosmic rays per square centimeter per second, depending on solar activity and location. That's because Earth's magnetic field and atmosphere normally block most of them. Over time, this higher flux adds up. Each hit has a small chance of causing cancer or other damage. More hits means higher probability. Astronauts on the ISS, who are partially protected by Earth's magnetic field, still receive radiation doses about 150 to 200 times higher than on the ground. A 6-month stint on the station increases lifetime cancer risk by about 1%. That might not sound like much, but it's 1% added to whatever baseline risk you already have. For a young astronaut with decades of life ahead, that's meaningful. And that's in low Earth orbit, with partial protection from the magnetic field. Beyond Earth's magnetic field, in deep space, the radiation environment is worse. NASA has estimated that a round trip to Mars, about 18 months to 2 years total mission time, would expose astronauts to radiation doses that increase cancer risk by about 5%. 5% added risk. That's considered on the edge of acceptable for trained volunteers who understand what they're signing up for. But it's far from safe. And Mars is relatively close. A mission to the outer solar system would take years. More time in deep space means more accumulated radiation dose, more cancer risk, more potential for other radiation effects like cataracts, cardiovascular damage, central nervous system effects. There's evidence that radiation exposure can affect cognitive function. Studies on animals exposed to cosmic ray analogs show changes in brain structure and behavior. Memory impairment, reduced problem-solving ability, increased anxiety. Whether these effects occur in humans from space, radiation exposure is still being studied. But it's a concern for long-duration missions. You can't have astronauts on a multi-year mission developing cognitive problems. The crew needs to stay sharp, able to make complex decisions, respond to emergencies, complete their mission. Radiation-induced cognitive decline could be catastrophic. Shielding helps, but not as much as you might think. You'd assume that thick walls would block radiation. And they do, to an extent. But cosmic rays are so energetic that they can penetrate meters of material. Practical spacecraft can't carry that much shielding. Every kilogram of mass has to be launched from Earth. More mass means more fuel needed, more cost. There's a limit to how much shielding is feasible. Current spacecraft have thin aluminum hulls, maybe a few millimeters thick. This provides almost no protection against cosmic rays. It blocks some solar particles, but cosmic rays punch right through. You could add thicker shielding, maybe water tanks surrounding the crew compartment. Water is actually better shielding than metal for cosmic rays because it doesn't produce as many secondary particles. When a cosmic ray hits aluminum, it can shatter aluminum nuclei, creating showers of secondary particles that spread out and cause more damage. Water or hydrogen-rich materials absorb energy without producing as many secondaries. But you'd need meters of water to significantly reduce cosmic ray dose. That's thousands of kilograms of extra mass. Difficult to launch. Difficult to manage in zero gravity. So spacecraft designers face a trade-off. Better shielding means more mass, more cost, more complexity. Less shielding means higher radiation exposure. Current designs accept some radiation exposure as unavoidable and try to minimize it within practical constraints. This is why deep space missions are planned with radiation in mind. Timing missions to coincide with solar minimum, when solar activity and particle radiation is lower. Designing spacecraft with storm shelters, areas with extra shielding where crew can go during solar particle events. Limiting mission duration to keep total dose within acceptable limits. But there's no way to eliminate the risk entirely. Space is radioactive. It's constantly bathed in high-energy particles from cosmic sources. Any human in that environment will be exposed. Any extended stay in deep space will accumulate significant dose. This isn't a problem you can engineer around completely with current technology. You can mitigate it. You can reduce it. But you can't eliminate it. And for an unprotected person in space, the radiation exposure would be massive. Not enough to cause immediate radiation sickness in the seconds before other effects become fatal. Radiation sickness requires high acute doses, usually absorbed over hours or days, but enough that if they somehow survive the pressure and oxygen problems, the radiation alone would guarantee severe health effects or death within days to weeks. In space, there's no protection. The radiation hits you directly. Solar radiation includes ultraviolet light, which causes sunburn and skin cancer with prolonged exposure. In space, without atmospheric filtering, UV exposure would be intense. But UV is actually the least of your concerns. The real danger comes from ionizing radiation. High-energy particles moving at significant fractions of the speed of light. Galactic cosmic rays are atomic nuclei, mostly protons and helium nuclei, but also heavier elements, accelerated to enormous energies by supernova explosions and other violent cosmic events. These particles have energies millions of times higher than anything we can produce in particle accelerators on Earth. When they hit biological tissue, they tear through cells, breaking molecular bonds, damaging DNA, creating cascades of secondary particles. The damage is immediate and cumulative. A single high-energy cosmic ray passing through your body might hit a few cells along its path. Each hit has a chance of causing mutations, potentially leading to cancer. Over time, repeated exposure to cosmic rays accumulates damage. Astronauts on the International Space Station receive radiation doses about 150 to 200 times higher than people on the ground. They're partially protected by Earth's magnetic field, since the station orbits within that field. But even so, they receive much higher doses than we do. Long-duration missions on the ISS, 6 months or more, result in measurable increases in cancer risk. Beyond Earth's magnetic field, in deep space, the radiation exposure is even higher. Astronauts on a mission to Mars would receive radiation doses during the journey that significantly increase their lifetime cancer risk. There's no way to completely shield against cosmic rays with current technology. The particles are too energetic. Thick shielding can help, but it's heavy and impractical for spacecraft. Some shielding materials can actually make things worse by creating secondary radiation when cosmic rays hit the shield material. And this is for astronauts inside spacecraft with some level of shielding. A person directly exposed to space with no protection would receive massive radiation doses. Not enough to cause immediate radiation poisoning in the few seconds before death from other causes, but enough to guarantee severe damage if they somehow survived the pressure and oxygen problems. The radiation would continue to damage tissue, destroying cells, causing burns, leading to organ failure. There's also solar particle events to consider. Occasionally, the Sun releases bursts of charged particles during solar flares and coronal mass ejections. These events can deliver radiation doses high enough to cause acute radiation sickness within hours or days. A solar particle event hitting an unprotected person in space would be catastrophic. Even inside a spacecraft with thin aluminum walls, a major solar particle event can be dangerous. This is why solar activity is carefully monitored during space missions. During the Apollo missions to the Moon, astronauts were at risk from solar particle events because they were beyond Earth's magnetic field. They were fortunate that no major events occurred during their missions. A large solar flare during an Apollo mission could have exposed the crew to lethal radiation doses. Planning for future missions to Mars or deeper space has to account for this risk. Spacecraft need radiation shelters, areas with extra shielding where crew can retreat during solar events. But again, for an unprotected person exposed directly to space, solar particle events are just one more item on a long list of things that will end you. Let's talk about what actually happens to a human body in the first minute of exposure. We can piece this together from animal experiments, from accidental exposures in vacuum chambers, from physics and physiology. 0 seconds. Exposure begins. The pressure drops instantly from 1 atmosphere to near 0. 1 second. Gas in the lungs begins to expand. If breath was being held, lung tissue starts to tear. If exhaling, air rushes out. Saliva on the tongue begins to boil. Moisture on the eyes begins to evaporate. 2 seconds. Ebulism begins in earnest. Dissolved gases start forming bubbles in blood and tissues. Skin begins to swell as subcutaneous gases expand. 4 seconds. Water vapor from boiling moisture cools the mouth and nasal passages, causing a brief sensation of cold. The swelling becomes pronounced. 6 seconds. Circulation becomes compromised as gas bubbles interfere with blood flow. 8 seconds. Oxygen in the bloodstream is being consumed by the brain and organs. No new oxygen is entering because the lungs are empty. 10 seconds. Oxygen levels in the brain drop below the threshold needed to maintain consciousness. Vision begins to narrow. Hearing fades. 12 seconds. Consciousness is lost. The person is now unconscious, unable to experience what happens next. 10 seconds. The heart is still beating, trying to pump blood that's increasingly full of bubbles. Brain activity is declining rapidly from oxygen deprivation. 30 seconds. Severe tissue swelling throughout the body. The person would be visibly bloated if anyone were watching. Blood pressure is erratic due to the compromised circulation. 60 seconds. Brain damage from oxygen deprivation is becoming irreversible. Even immediate rescue and repressurization at this point would likely result in severe neurological impairment. 90 seconds. Cardiac function is failing. The heart might still be beating, but weakly and irregularly. Brain activity has mostly ceased. 2 minutes. Clinical death. No heartbeat, no brain activity, no chance of revival. This timeline assumes exposure to pure vacuum in deep space. In partial vacuum or with brief exposure, followed by immediate rescue, some of these effects might be less severe or slower to develop. There are documented cases of people surviving exposure to near vacuum for very brief periods. In 1965, A technician at the Johnson Space Center was testing a spacesuit in a vacuum chamber when the suit failed. He was exposed to near-vacuum conditions for about 14 seconds before the chamber could be repressurized. He described feeling the saliva on his tongue boiling. Then, he lost consciousness. When the chamber was repressurized, he regained consciousness and recovered fully with no lasting damage. 14 seconds. That's about the limit of survivable exposure. And that's with immediate rescue, immediate repressurization, and immediate medical attention. In actual deep space, there's no immediate rescue. There's no chamber to repressurize. You're in an infinite vacuum. Without a spacecraft nearby, without a suit, you're not surviving. Period. There's also the question of what happens to a body in space over longer time periods. If someone were to pass in space and their body was left there, what would happen? On Earth, bodies decompose through several processes. Bacteria, both from the environment and from the body itself, break down tissue. Insects consume tissue. Oxidation and moisture contribute to decay. In space, most of these processes don't work. There are no bacteria in the vacuum of space, no insects. But there are bacteria inside the body, in the gut and other areas. After death, these bacteria would continue to break down tissue for a time, producing gases. But without atmospheric pressure to contain them, those gases would escape into space. The body would desiccate, losing all moisture through sublimation. Sublimation is when a substance goes directly from solid to gas without passing through a liquid phase. In vacuum, ice sublimates. The frozen water in tissues would slowly sublimate away. Over time, you'd be left with a freeze-dried corpse. If the body was in sunlight, the sunward side would heat up, potentially causing some decomposition from heat. The shadow side would remain frozen. If the body was far from any star, it would freeze solid and remain frozen indefinitely. Temperature extremes and radiation would gradually break down organic molecules. UV radiation from any nearby star would cause chemical changes in exposed tissue. Cosmic rays would continue to hit and damage molecular structures. Over millions of years, the body would slowly break down into component molecules and atoms. But in the short term, over years or decades, a body in space would remain largely intact, frozen and desiccated, but recognizable. This is morbid to think about, but it illustrates just how different the space environment is from Earth. The normal processes of life and death that we take for granted simply don't apply in the same way. Now, let's talk about the engineering challenges of keeping humans alive in this environment. Because we do send people to space. We do keep them alive. But it requires extraordinary technology and constant vigilance. A spacesuit is essentially a tiny personal spacecraft. It has to provide everything the human inside needs to survive. Pressure. A spacesuit maintains internal pressure, typically about 4.3 pounds per square inch for NASA's current suits. That's lower than Earth's atmospheric pressure, but high enough to prevent embolism and allow the person to breathe. Lower pressure means the suit can be less rigid and easier to move in. But you can't go too low, or the oxygen partial pressure becomes insufficient. The partial pressure of a gas is the contribution that gas makes to total pressure. In Earth's atmosphere, oxygen makes up about 21% of the air. At 1 atmosphere total pressure, that's about 3 pounds per square inch of oxygen partial pressure. Your lungs need at least about 2.5 pounds per square inch of oxygen to function properly. Go below that, and you develop hypoxia, oxygen starvation. So, a spacesuit operating at 4.3 psi total pressure uses pure oxygen to maintain adequate partial pressure. All oxygen, no nitrogen. This simplifies the system and keeps the suit pressure low enough to be mobile. But it creates other challenges. Pure oxygen is a fire hazard. Any spark, any heat source, can ignite materials that wouldn't burn in normal air. This was tragically demonstrated in the Apollo 1 fire in 1967. 3 astronauts were conducting a test inside the command module on the launch pad. The cabin was pressurized with pure oxygen at about 16 psi, higher than atmospheric pressure. A spark from faulty wiring ignited materials inside the cabin. In the pure oxygen high-pressure environment, the fire spread instantly. The cabin filled with smoke and flames in seconds. The astronauts couldn't escape because the hatch design required pressure equalization before it could open. They were overcome by smoke and heat before the hatch could be opened from outside. All 3 perished. Virgil Grissom, Edward White, and Roger Chaffee. Experienced astronauts, test pilots, engineers. Gone in less than a minute because of a fire that wouldn't have been nearly as dangerous in normal air. The tragedy led to major design changes. New materials that don't burn easily, even in pure oxygen. New hatch designs that can be opened quickly. New safety protocols. But it demonstrated the dangers of pure oxygen environments. Current spacesuits mitigate this risk by using lower pressure. At 4.3 psi, materials are less likely to ignite than at 16 psi. But astronauts still have to be careful. No open flames. Careful attention to any potential ignition sources. Continuous monitoring for any sign of fire. Because in a suit, there's no escaping. You're sealed in. A fire inside your spacesuit would be immediately lethal. Oxygen supply is another critical system. The suit has to continuously provide fresh oxygen and remove carbon dioxide. Oxygen tanks carry compressed O2, released at a controlled rate to maintain pressure. The astronaut breathes this oxygen, then exhales carbon dioxide. Without removal, CO2 would build up, becoming toxic within minutes. Current suits use lithium hydroxide canisters. These chemical compounds react with carbon dioxide, absorbing it from the air. The reaction is simple. Lithium hydroxide plus carbon dioxide produces lithium carbonate plus water. The CO2 is chemically bound into a solid compound, removed from the air. But lithium hydroxide canisters have limited capacity. Once they're saturated with CO2, they stop working. You have to replace them. For a typical spacewalk, lasting 6 to 8 hours, the suit carries enough canisters to scrub CO2 for the entire duration with some margin. But if a spacewalk runs long, if something goes wrong and the astronaut can't get back inside, they could run out of scrubbing capacity. CO2 would build up. The astronaut would start feeling dizzy, confused, short of breath. Eventually, they'd lose consciousness. This came close to happening during some early spacewalks when procedures took longer than planned. Now there's more margin built in. Longer rated canisters. Backup systems. Strict time limits on spacewalks. But the fundamental limitation remains. The suit can only support you for so long before consumables run out. Temperature control is another major challenge. In the vacuum of space, you can't lose heat through convection or conduction. Only radiation. But the human body generates heat constantly. About 100 watts when resting. More when working. In a sealed suit, that heat has nowhere to go. Without cooling, you'd overheat within minutes. Hypothermia, heat exhaustion, heat stroke. Modern suits use a liquid cooling garment worn against the skin. It's basically underwear with tubes woven through it. Cool water flows through the tubes, absorbing heat from your body. The water circulates to a heat exchanger in the suit's backpack. There, the heat is radiated away into space. This system works well, but it's complex. Pumps to circulate water. Heat exchangers with large surface area to radiate heat efficiently. Temperature sensors and controls. If the cooling system fails, the astronaut has maybe 10 to 15 minutes before heat buildup becomes dangerous. There have been cases of cooling system malfunctions during spacewalks, usually caught quickly and addressed. Return to the airlock. Switch to backup cooling. But it's another single point of failure. Another system that has to work perfectly, or the consequences are severe. The suit also has to protect against direct sunlight. In space, sunlight is intense. No atmosphere to scatter or absorb it. The solar constant, the amount of solar energy hitting a surface perpendicular to the sun, is about 1,360 watts per square meter. That's about 1.8 horsepower per square meter. A spacesuit in direct sunlight absorbs some of this energy. The outer layer is designed to be reflective. White material that reflects most of the visible and infrared light. But some energy still gets through. The temperature difference between the sunlit side of a suit and the shadow side can be hundreds of degrees. Sunlit surface might reach 250 degrees Fahrenheit or 120 degrees Celsius. Shadow side might be minus 150 degrees Fahrenheit or minus 100 degrees Celsius. The suit has to manage this temperature gradient. Insulation to prevent heat from conducting from the hot outer layer to the astronaut inside. The cooling system to remove both metabolic heat and any absorbed solar heat. It's a delicate balance. Too much cooling and the astronaut gets cold. Too little and they overheat. The system has to continuously adjust based on conditions. In sunlight or shadow. Working hard or resting. It's sophisticated engineering packed into a wearable package. Then there's mobility. A pressurized suit naturally wants to be a sphere. That's the shape that minimizes stress on the fabric. But a spherical suit is impossible to move in. You need joints. Shoulders, elbows, wrists, hips, knees, ankles. Each joint has to allow bending while maintaining pressure. This is solved with complex bearing and fabric designs. Joints that can articulate while keeping the seal. But even the best joints are stiff, fighting against the pressure, trying to keep the suit rigid. Moving in a spacesuit requires effort. Bending your elbow isn't just moving your arm. It's compressing the suit material against internal pressure, like trying to bend a partially inflated tire. Astronauts train extensively to learn how to move efficiently in suits, how to use leverage, how to minimize wasted motion. Even so, spacewalks are exhausting. 6 hours of work in a suit is far more tiring than 6 hours of work in normal conditions. Gloves are especially challenging. Hands need fine motor control. Astronauts have to manipulate tools, turn bolts, handle small objects. But pressurized gloves fight every movement. Gripping something requires overcoming the pressure, trying to keep your hand open. After hours of work, hand fatigue is common. Fingers cramping, muscles aching. Some astronauts have reported losing fingernails from the constant pressure of working in gloves. The nails lift away from the nail bed over time. Painful and debilitating. Better glove designs help. But the fundamental challenge remains. A pressurized glove will always resist movement. There's only so much that can be done. The current generation of NASA spacesuits, the extravehicular mobility units, are engineering marvels. But they're also heavy, expensive, and require constant maintenance. Each suit costs millions of dollars. They weigh about 280 pounds, fully configured. In the zero gravity of space, weight doesn't matter. But mass and inertia do. Moving that much mass requires effort. Stopping it requires effort. Momentum wants to keep you moving, even after you stop pushing. The suits are also old. Most of the current suits were built in the 1980s and 90s. They're refurbished, parts replaced, systems upgraded. But the basic design is decades old. NASA is developing new suits for future missions. Improved mobility, better interfaces, more modern materials. But developing a new spacesuit is expensive and time-consuming. It takes years of design, testing, certification, making sure every system works in every possible scenario, making sure there are no single-point failures that could endanger an astronaut. The complexity is enormous, more complex than most people realize. A spacesuit isn't just a protective shell. It's a complete life support system in a wearable package. Pressure, oxygen, cooling, power, communications, safety systems. All of it has to work together flawlessly. And all of it has to fit into something a person can wear and move in. One small malfunction, one seal failure, one pump breakdown, and the person inside is in immediate danger. This is the reality of working in space. Even with the best technology we can build, it's risky. Every spacewalk is planned meticulously. Every procedure tested and practiced. Every tool and part inspected. Backup plans for every possible failure mode. Multiple levels of redundancy. And even then, things go wrong sometimes. Suit leaks, cooling failures, torn gloves, visor contamination. Most of these are caught and dealt with before they become critical. But the potential is always there. Space doesn't forgive mistakes. It doesn't give second chances. One serious failure, and you have minutes at most to get back to safety. Often less. Oxygen. The suit continuously supplies oxygen to breathe. It also removes carbon dioxide that you exhale, usually with lithium hydroxide canisters that absorb CO2. Temperature control. The suit has cooling systems to remove the heat your body generates. In sunlight, it has reflective surfaces to prevent overheating. In shadow, it has insulation to prevent heat loss. A liquid cooling garment, worn under the suit, circulates cool water to remove excess heat. Radiation protection. The suit provides some shielding, but not much. The material can block some radiation, but cosmic rays and solar particles still get through. Spacewalks are scheduled to minimize time in space and to avoid solar particle events when possible. Mobility. The suit has to allow the wearer to move, to work, to manipulate tools. This is harder than it sounds because the pressure inside wants to inflate the suit into a rigid balloon shape. Joints are designed to bend despite the pressure. Gloves are especially challenging because hands need fine motor control. All of this packed into a suit that weighs about 280 pounds on Earth. Though, in the zero gravity of space, weight isn't an issue, just mass and inertia. A modern spacesuit is a marvel of engineering, but it's also bulky, restrictive, and expensive. Each suit costs millions of dollars. They require extensive maintenance. They can only support a person for a limited time, usually 6 to 8 hours per spacewalk. And they're not perfect. Spacesuit failures have occurred. Leaks, cooling system failures, visor fogging, glove damage. In most cases, the astronaut was able to return to the spacecraft before the problem became critical. But there have been close calls. In 2013, Italian astronaut Luca Parmitano was on a spacewalk when water began leaking into his helmet. The water came from the cooling system. It accumulated in his helmet, floating in zero gravity, covering his face. He couldn't see. He couldn't breathe properly. Water was getting into his nose and mouth. He had to abort the spacewalk immediately and get back inside. The leak continued as he made his way back, more water accumulating. By the time he got inside and the helmet was removed, there was over a liter of water floating in the helmet. He came very close to drowning in his own spacesuit. A terrifying reminder that even with the best technology, space is unforgiving. One small failure and you're in trouble. Inside a spacecraft, the situation is better, but still precarious. The spacecraft provides a pressurized environment, usually close to Earth's atmospheric pressure or slightly lower. It supplies oxygen and removes carbon dioxide with sophisticated life support systems. It maintains temperature through active heating and cooling. It provides some radiation shielding, though not enough to fully protect against cosmic rays. But spacecraft are fragile. The hull is thin, usually just a few millimeters of aluminum or composite material. It has to be thin to keep weight down for launch. Mass is the enemy of spaceflight. Every kilogram of spacecraft mass requires fuel to launch it. More mass means more fuel. More fuel means more fuel to lift the fuel. It's called the rocket equation, and it's merciless. The payload that reaches orbit is a tiny fraction of the total launch mass. For a typical rocket, maybe 3 to 5% of the launch mass makes it to orbit. The rest is fuel and structure that gets discarded along the way. This means spacecraft have to be as light as possible. Engineers shave grams wherever they can. Thinner walls, lighter materials, minimal structure. The International Space Station modules have walls about 3 millimeters thick in most areas. That's about 1/8 of an inch. Thin, aluminum, or composite material. Enough to hold pressure. Enough to provide minimal shielding against small debris. But not much more. This thin hull is all that stands between the crew and the vacuum of space. A micrometeorite, a tiny piece of rock moving at tens of thousands of miles per hour, could puncture it. Space debris, fragments from old satellites or rocket stages, could hit it. Even a paint flake, traveling at orbital velocity, has enough energy to damage the hull. At orbital speeds, kinetic energy scales, with velocity squared, something moving at 4.85 miles per second, typical orbital velocity, has enormous kinetic energy, even if it's small. A paint flake, a few millimeters across, hitting at that speed, carries as much energy as a bullet. It can chip or crack windows. It can puncture thin metal. The ISS has been hit by debris many times. Small impacts that created pits and craters in the hull, scratches and chips on windows. So far, nothing has caused a serious breach. But it's a constant concern. Debris, tracking systems, monitor known objects. The station maneuvers to avoid larger pieces when they're predicted to come close. But you can't track everything. Anything smaller than about 10 centimeters is too small to track reliably, yet still large enough to cause catastrophic damage. The crew lives with the knowledge that at any moment, an untracked piece of debris could hit, could puncture the hull, could cause rapid depressurization. It's a low probability event, but not zero probability. And in space, low probability doesn't mean safe. It means you might get lucky. The station also has shielding designed to protect against smaller impacts. Whipple shields, layers of material spaced apart. A small object hits the outer layer, shatters into fragments. Those fragments spread out and hit the next layer with less energy per fragment. Multiple layers break up and slow down the impact. It works well against small, fast-moving particles. But there's a limit. Something too large or too fast will penetrate all the layers. And again, mass constraints limit how much shielding can be added. More shielding means more mass, more cost to launch and maintain orbit. It's a trade-off between protection and practicality. Current designs accept some risk as unavoidable. Life support systems on a spacecraft are more sophisticated than a spacesuit, but operate on the same principles. Provide oxygen, remove carbon dioxide, maintain pressure, manage temperature and humidity, recycle water. The ISS has life support systems that recycle about 90% of water. Urine, sweat, condensation from the air, all collected and purified. Run through filters and purification systems until it's clean enough to drink. It sounds unpleasant, but it's necessary. Water is heavy. Launching water to orbit costs thousands of dollars per kilogram. Recycling water in orbit is far more economical than constantly resupplying it. The astronauts drink recycled water every day. They joke that today's coffee was yesterday's urine. It's true. But the purified water is actually cleaner than most tap water on Earth. The purification systems are that good. Air is also recycled. Oxygen is extracted from water through electrolysis. Pass an electric current through water and it splits into hydrogen and oxygen. The oxygen goes into the cabin atmosphere. The hydrogen is either vented or combined with carbon dioxide to produce water again. This is the Sabatier reaction, named after the French chemist who discovered it. Carbon dioxide plus hydrogen produces methane and water. The methane is vented overboard. The water is reclaimed and electrolyzed again. It's a closed-loop system. Almost. Some water is lost to inefficiencies. Some air escapes through tiny leaks. Resupply missions bring fresh water and oxygen to make up the losses. But the recycling reduces the amount that needs to be launched by an order of magnitude. For a mission to Mars or beyond, where resupply isn't possible, these systems have to be even more efficient. You'd need to recycle 98 or 99% of everything. Lose too much, and you run out before reaching your destination. Current technology can approach these levels, but maintaining it over months or years is challenging. Systems break down, filters clog, pumps fail, sensors drift out of calibration. On the ISS, broken systems can be replaced with parts from resupply missions. On a Mars mission, you'd have to carry spare parts for every possible failure, and hope nothing breaks that you don't have a spare for. Spacecraft also have to manage waste. Food wrappers, packaging, broken equipment, everything that accumulates from daily life. On the ISS, garbage is packed into empty cargo vessels. The vessels undock and burn up in the atmosphere, a convenient way to dispose of trash. On a deep space mission, you can't do that. You'd have to store waste or recycle it somehow. Organic waste could potentially be composted or broken down. But plastics, metals, broken electronics, these accumulate. Years of mission could generate tons of waste. Where do you put it? You can't just throw it overboard. It would become space debris. You'd have to keep it on board. Find space to store it. Accept the added mass. Or develop systems to recycle materials, breaking them down to raw elements and rebuilding what you need. That's theoretically possible, but it's complex and energy-intensive. No one has demonstrated a complete recycling system that can handle all waste types. It's a challenge that has to be solved for long-duration missions. Temperature management in space is also counterintuitive. You might think space is cold, so keeping warm would be the main problem. But spacecraft actually have trouble getting rid of heat. All the electronics, all the human bodies, all the systems running constantly generate heat. In the vacuum of space, that heat can only be radiated away. Spacecraft have large radiators, panels that radiate heat into space. The ISS has huge radiator panels, clearly visible in photographs. They glow faintly in infrared from the heat they're radiating. If those radiators fail or are damaged, the station would overheat. Temperatures would rise until electronic systems shut down or catch fire. The crew would have to evacuate. This nearly happened in 2013 when an ammonia leak threatened the cooling system. Ammonia circulates through the radiators, carrying heat from inside the station to the radiator panels. If the ammonia leaks, the cooling system stops working. The crew had to do emergency spacewalks to fix the leak and replace cooling pumps. It was a close call. Hours of intense work in spacesuits. Multiple crew members outside simultaneously. Higher risk than a normal spacewalk. But necessary because without cooling, the station would become uninhabitable. They fixed it. But it demonstrated how fragile these systems are. One leak, one failed pump, and you're in trouble. Now, scale this up to a Mars mission. 6 to 9 months to get there. Same duration on the surface. 6 to 9 months to get back. 2 to 3 years total. All the life support systems have to work perfectly for that entire time. No resupply. No rescue. If something breaks, the crew has to fix it with whatever parts and tools they have. If they can't fix it, the mission fails. Maybe the crew dies. This is why mission planning is so detailed. Every possible failure mode is analyzed. Redundancy is built in wherever possible. 2 of every critical system. So if one fails, you have a backup. Spare parts for components that might wear out. Tools and materials for repairs. Detailed procedures for diagnosing and fixing problems. Training so the crew knows how to handle emergencies. But you can't plan for everything. Unknown unknowns. Failures you didn't anticipate. Combinations of problems that interact in unexpected ways. Apollo 13 is the classic example. An oxygen tank exploded in the service module, not during launch or re-entry, where you might expect problems. But during the cruise to the moon, when everything should have been routine, a simple electrical fault caused a fire in the tank. The tank ruptured. Oxygen vented into space. The service module's power and life support systems failed. The crew had to abandon the main spacecraft and retreat to the lunar module, a 2-person lander designed for short surface stays. They used it as a lifeboat for 3 people for 4 days, stretching consumables far beyond design limits, rigging systems together in ways never intended, rationing power, rationing water, freezing in the cold, carbon dioxide building up because they didn't have enough lithium hydroxide canisters. They had to jury-rig a solution using duct tape and spare materials to adapt the command module canisters to work in the lunar module. It worked. They made it back, splashed down safely. All 3 survived, but it was close. Multiple times during the crisis, they were hours away from running out of something critical. Power, water, breathable air. They made it through a combination of skill, ingenuity, and luck. Not every mission would be so fortunate. In deep space, far from Earth, an Apollo 13 scenario could easily be fatal. No quick return. No mission control with rooms full of engineers working the problem. Communication delays measured in minutes or hours. The crew would be on their own. This brings up another aspect of deep space missions that's often overlooked. Psychological challenges. Being confined in a small spacecraft for months or years. Knowing you're millions of miles from home. Knowing there's no rescue coming if things go wrong. The stress would be immense. Even on the ISS, where crews are only a few hours from Earth, where they can see their home planet outside the window, where they can talk to family in real time, psychological stress is a concern. Astronauts are carefully selected for psychological stability. They undergo extensive evaluation. Psychological support is provided during missions. Regular communication with psychologists on the ground. Scheduled time for recreation and personal activities. Careful attention to crew dynamics. Even so, there are challenges. Conflicts between crew members. Feelings of isolation, depression, sleep disturbances. These are managed, but not eliminated. On a Mars mission, it would be worse. Communication delays mean you can't have real-time conversations with family. You send messages and wait minutes, or tens of minutes for responses. It's asynchronous communication. Email, not phone calls. You're watching Earth recede in the distance, getting smaller. Eventually, so far away, it's just another star. The sun itself gets dimmer as you move outward. At Mars, sunlight is only about 43% as intense as at Earth. At Jupiter, it's 4%. At Saturn, 1%. Beyond that, the Sun is just a very bright star. Cold, dark, isolated. Months or years in that environment would test anyone's mental health. Studies on Earth analogues, people spending months in isolated habitats to simulate space missions, show that psychological stress is one of the biggest challenges. Interpersonal conflicts, difficulty maintaining motivation, struggles with the monotony. And these are on Earth, where participants know they can leave if they really need to, where rescue is available if there's a medical emergency. In actual deep space, there's no leaving, no rescue. You're committed for the duration. If you develop serious psychological issues, depression, psychosis, what happens? The rest of the crew has to manage it. There's limited medical support on board. Probably some psychiatric medications. Maybe telemedicine consultations with delays. But if someone becomes a danger to themselves or the mission, options are limited. Restraint, sedation. Not good solutions. But there might not be better ones available. This is one of the least discussed but most serious challenges of long-duration spaceflight. We don't fully understand how people will respond psychologically to years in deep space. The longest anyone has spent in space continuously is about 14 months. Russian cosmonaut Valery Polyakov set that record on the Mir space station. 14 months in low Earth orbit. He did remarkably well, psychologically. But that's still much shorter than a Mars mission. And he was in regular communication with Earth. He could see his home planet. He knew people were close by. Deep space is different. The isolation is more profound. Some psychological experts worry that extended deep space missions could cause psychological breakdown in even well-selected crew members. That the stress might be fundamentally too much for humans to handle. Others think we'll adapt. That with proper support and preparation, people can handle years in space. We won't know until we try. And when we do try, when the first crew launches on a multi-year mission beyond Earth, they'll be the test case. Pioneers in every sense. Facing not just the physical challenges of surviving in a hostile environment, but the psychological challenges of isolation, confinement, and distance from everything familiar. It's a daunting prospect. This thin hull is all that stands between the crew and the vacuum of space. A micrometeorite impact, a piece of space debris, a manufacturing defect, any of these could create a hull breach. Depressurization. The air inside rushes out into space. In a catastrophic breach, complete depressurization could happen in seconds. In a smaller breach, it might take minutes. Either way, if not repaired quickly, it's fatal. This is why spacecraft have emergency protocols. Pressure suits, or at least oxygen masks for emergencies. Patch kits to seal small breaches. The ability to seal off compartments to isolate a breach. But in a major failure, these measures might not be enough. The history of spaceflight includes several depressurization incidents. In 1971, the Soviet Soyuz 11 mission ended in tragedy when a valve opened prematurely during descent. The spacecraft depressurized at high altitude while the crew was not wearing pressure suits. All 3 cosmonauts perished from asphyxiation before the capsule landed. It was a stark reminder that space doesn't tolerate mistakes. One small valve failure, and 3 trained, experienced cosmonauts were lost. Since then, protocols have changed. Crews now wear pressure suits during launch and re-entry. More redundancy in systems. More safety checks. But the fundamental risk remains. Space is hostile, and there's only so much engineering can do to protect against it. Let's zoom out and think about longer duration missions. The International Space Station is in low Earth orbit, only about 250 miles up. At that altitude, Earth's magnetic field still provides significant protection from radiation. The astronauts are mostly shielded from solar particles and get reduced cosmic ray exposure. They're close enough that resupply missions can arrive regularly, with fresh food, water, spare parts, everything needed to maintain the station. They're close enough that in an emergency, they can return to Earth within hours. But imagine a mission to Mars. The journey takes 6 to 9 months each way, depending on the orbital alignment. During that journey, the crew is in deep space, beyond Earth's magnetic field. Full cosmic ray exposure. Risk from solar particle events. No quick return if something goes wrong. No resupply missions. The spacecraft has to carry everything needed for the entire mission. Water, food, spare parts, medical supplies, life support systems have to function flawlessly for years. Any major failure could be catastrophic. The psychological challenges are immense. Confined to a small spacecraft for months. Knowing that Earth is getting farther away and there's no turning back. The communication delay increases as the distance grows. At Mars' closest approach to Earth, light takes about 3 minutes to make the trip. That's a 6-minute round trip for any communication. Ask a question and wait 6 minutes for an answer. At Mars's farthest distance, the delay is over 20 minutes each way. That's a 40+ minute round trip. No real-time conversations. No immediate help from mission control. The crew has to handle problems themselves. The radiation exposure alone is a major concern. Estimates suggest a round trip to Mars would expose astronauts to radiation doses that increase their lifetime cancer risk by several percentage points. That's considered acceptable for trained volunteers who understand the risks. But it's far from safe by normal standards. And that's with the best shielding we can currently provide. Then, there's the question of missions beyond Mars, to the outer solar system, to the moons of Jupiter and Saturn. These missions would take years or decades with current propulsion technology. The challenges multiply. Longer exposure to radiation. Longer time in zero gravity, which causes bone loss and muscle atrophy. Longer isolation from Earth. Greater risk of system failures, simply because there's more time for things to go wrong. The psychological toll of spending years in a confined space with the same small group of people. And these are all challenges for trained astronauts with the best technology we can build. For ordinary people, the challenges would be insurmountable. There's been talk of space tourism, of commercial spaceflight, of regular people going to space. Some of this is already happening. Short suborbital flights that reach the edge of space for a few minutes. Trips to the International Space Station for wealthy tourists who can afford the tens of millions of dollars for a ticket. But these are brief, controlled experiences. The participants undergo medical screening and training. They're accompanied by professionals. The spacecraft are designed with extensive safety systems. And even so, there's risk. Any spaceflight carries risk that can't be completely eliminated. The idea of regular, routine spaceflight for ordinary people, the kind of casual space travel you see in science fiction, that's not close to reality. Not with current technology. Not for many decades at minimum. The space environment is too hostile. The engineering challenges too severe. The costs too high. Space will remain the domain of trained professionals, highly selected individuals, and very wealthy adventurers willing to accept significant risks. There's also the philosophical question of why we go to space at all, given these risks. Why send people into such a hostile environment? What's worth the danger? For exploration, for scientific research, robotic missions can do most of what we need. Probes and rovers can go places humans can't, can stay for years or decades, can withstand radiation and temperature extremes that would be lethal to people. The argument for human spaceflight is usually that humans can adapt, can make decisions, can respond to unexpected situations in ways that robots can't. There's truth to that. But it's also true that keeping humans alive in space is enormously expensive and complex. Every kilogram of food, water, and oxygen that has to be launched. Every system needed for life support. Every safety measure and backup system. All of this adds weight, cost, and complexity. For many missions, robots are simply more practical. The case for human spaceflight often comes down to inspiration, to the sense of adventure, to the symbolic importance of humans exploring beyond Earth. These are valid reasons. But they're not purely practical reasons. They're about what we value as a species, about what gives us meaning and purpose. And there's another argument. Long-term survival of humanity. Earth won't last forever. The sun will eventually expand and destroy the inner planets. That's billions of years away. The sun is about halfway through its main sequence lifetime. It has another 5 billion years or so before it starts running out of hydrogen in its core. When that happens, it will swell into a red giant. The outer layers will expand past Earth's current orbit. Our planet will be consumed, vaporized. But long before that, Earth will become uninhabitable. As the sun ages, it gradually gets brighter, about 10% brighter per billion years. In about 1 billion years, maybe a bit more, the sun will be bright enough that Earth's oceans will start to evaporate. The water vapor will escape into space. Earth becomes a dry, sterile planet, too hot for life. That's the long-term natural fate. But there are also shorter-term catastrophes to consider. Asteroid impacts. A large asteroid, 6.2 miles across, like the one that contributed to the dinosaur extinction, hits on average every 100 million years or so. The last one was 66 million years ago, so we're not overdue, but it could happen any time. If it happened tomorrow, if a 6.2-mile asteroid hit Earth, the consequences would be catastrophic. The impact would release energy equivalent to billions of nuclear weapons, vaporize rock, throw debris into the atmosphere, block out the sun for months or years, collapse the food chain. Most large animals would perish, including probably humans. Maybe some people would survive in bunkers or isolated locations. But civilization would collapse. Billions would be gone within months. We can detect and track large asteroids. If we saw one coming, we might have years or decades of warning, long enough to attempt a deflection mission. Slam a spacecraft into it to change its orbit slightly, or use a nuclear explosion near it to nudge it off course. We've never tried this on a real threat, but the physics suggests it could work if we have enough warning. But smaller asteroids, a few hundred meters across, those are harder to track. We don't have a complete catalogue of them. One could hit with little warning. Not an extinction event, but regional devastation. Destroy a city, cause tsunamis, kill millions. Then there's supervolcano eruptions. Earth has several supervolcano systems. Yellowstone is the most famous. A caldera formed by past eruptions. It erupts roughly every 600,000 years. Last eruption was 640,000 years ago. So again, not overdue, but it could happen. A Yellowstone eruption would be catastrophic. Ash covering much of North America. Volcanic gases cooling the climate globally. Agriculture disrupted. Potentially billions facing starvation. Human-caused catastrophes are also possible. Nuclear war. Engineered pandemics. Runaway climate change. Advanced AI systems that malfunction or act against human interests. Nanotechnology gone wrong. There are many ways civilization could be severely damaged or destroyed. Some are natural, inevitable on geological timescales. Others are risks we've created ourselves through technology. The argument for spacefaring civilization is that spreading to multiple worlds provides resilience. If something happens to Earth, humanity continues elsewhere. This makes sense from a species survival perspective. But it's a long-term view, thinking in terms of centuries or millennia, maybe millions of years. The challenge is that establishing self-sufficient colonies on other worlds is enormously difficult. Mars is the most often discussed option. It's relatively close. It has a day length similar to Earth's. It has polar ice caps with water. It has carbon dioxide in the atmosphere that could be processed. It has minerals and resources that could support industry. But it's also incredibly hostile. Atmosphere is less than 1% of Earth's pressure. Mostly carbon dioxide. Unbreathable. Temperature averages -80 degrees Fahrenheit or -62 degrees Celsius. Can reach +70 degrees Fahrenheit or 20 degrees Celsius at the equator during summer days, but drops to -200 degrees Fahrenheit or -130 degrees Celsius at the poles in winter. Radiation levels are high. No magnetic field to deflect cosmic rays. Thin atmosphere provides minimal shielding. Surface radiation doses are about 250 times higher than on Earth. Anyone living on Mars would need shielding. Underground habitats or structures covered with meters of regolith. Dust storms can cover the planet for months. Block out the sun. Disrupt solar panels. Reduce visibility to near zero. Gravity is about 38% of Earth's. That might sound livable, but we don't know what long-term low gravity does to human health. The ISS is zero gravity. Astronauts lose bone density and muscle mass. They have to exercise hours every day to minimize the loss. Even so, they come back weaker. Vision problems from fluid shifts in zero gravity. Immune system changes. It takes months to fully recover after returning to Earth. Mars has some gravity, so maybe the health effects would be less severe. But we don't know. No one has spent extended time in partial gravity. It's possible that Mars' gravity is enough to maintain health. It's also possible that it's not. That living on Mars for years would cause progressive bone loss, muscle atrophy, maybe other problems we haven't anticipated. We won't know until people try it. And the people who try it will be taking significant health risks. Establishing a self-sufficient Mars colony is a challenge that goes beyond just getting people there. You need to produce food. Grow crops in Martian regolith, which lacks the organic matter and beneficial microbes found in Earth soil. You'd need to add nutrients, manage water carefully, provide light and warmth. Greenhouses on Mars would have to be pressurized and climate-controlled. Significant infrastructure. You need to produce oxygen and water. Extract water from ice. Purify it. Electrolyze it for oxygen. You need energy. Solar panels could work, but Mars gets less sunlight than Earth. Dust storms block the sun for months. Nuclear reactors might be necessary, but launching and maintaining them is complex. You need manufacturing capability, spare parts, tools, building materials. You can't rely on Earth to send you everything you need. The transport costs are too high. The delays too long. You'd need to manufacture things locally. That requires raw materials, refining capabilities, fabrication equipment, skilled workers. Building up that industrial base from scratch would take decades. You need medicine and medical care. Injuries and illnesses will happen. You can't evacuate someone to Earth for surgery. They'd die during the 6-month journey. Medical facilities on Mars would have to handle everything. Trauma, surgery, chronic diseases, childbirth, if the colony is reproducing. Training doctors and stocking supplies for every medical eventuality is daunting. And you need social and political stability. A colony of hundreds or thousands of people living in confined habitats, under constant stress from the hostile environment, dependent on technology that can't be allowed to fail. That's a recipe for conflict. Disputes over resources, governance, priorities, psychological stress leading to interpersonal problems. Maybe violence. Colonies would need robust systems of governance, conflict resolution, mental health support. All of this is in addition to the basic survival challenge. Keep the air breathable. Keep the water clean. Keep the habitats pressurized. Keep the radiation shielding intact. Any one of these systems failing could threaten the entire colony. This is why Mars colonization, while possible in principle, is far more difficult than popular depictions suggest. It's not like settling the American frontier, where pioneers could live off the land with minimal technology. Mars requires constant, high-tech life support. One generation of colonists couldn't build it all. It would take many generations, continuous support from Earth, massive investment of resources. And even then, success isn't guaranteed. The colony could fail. Equipment breaks down. Supplies run out. A disaster strikes, that exceeds the colony's ability to respond. Everyone perishes, or the colony limps along, barely surviving, unable to grow or become self-sufficient. Dependent on Earth forever. That's not resilience. That's just an outpost. For a Mars colony to truly provide species insurance, it has to be fully self-sufficient, capable of surviving and thriving, even if contact with Earth is lost. That's a much higher bar, and we're nowhere near achieving it yet. Beyond Mars, the challenges only multiply. The moons of Jupiter and Saturn are mentioned as potential habitats. Europa, Enceladus, Titan. These worlds have water or even possible subsurface oceans, but they're far from the Sun. Jupiter is 5 times farther from the Sun than Earth. Saturn is 10 times farther. Sunlight is weak. Solar panels wouldn't provide enough power. You'd need nuclear reactors. Temperatures are extremely cold. Europa's surface is about -270 degrees Fahrenheit or -168 degrees Celsius. Titan is similar. Radiation around Jupiter is intense. The planet's magnetic field traps charged particles. Europa's orbit passes through radiation belts. Surface radiation doses would be lethal within days. You'd have to live deep underground or under thick ice. And getting there takes years. The trip to Jupiter takes about 6 years with current propulsion. To Saturn, about 7 years. All the challenges of a Mars mission amplified. These aren't realistic colonization targets with current or near-future technology. Maybe far-future advanced societies could establish outposts there. But for now, they're exploration destinations at best. Then there's the question of leaving the solar system entirely, going to other stars. This is where deep space becomes truly, incomprehensibly hostile. Interstellar space is the void between stars. Our closest stellar neighbor is Proxima Centauri, part of the Alpha Centauri system, 4.24 light-years away. That's about 25 trillion miles. At the speed of Voyager 1, our fastest spacecraft to leave the solar system, the trip would take about 70,000 years. Clearly impractical. You'd need much faster propulsion. Nuclear pulse propulsion, fission or fusion rockets, antimatter drives, laser-pushed light sails. These are theoretical concepts. Some have been studied in detail, but none have been built. Even optimistically, achieving 10% of light speed, which would cut the trip to 42 years, requires technology we don't have. Energy requirements are enormous. Accelerating a spacecraft to that speed takes energy. Slowing down at the destination takes more energy. The mass of fuel required is prohibitive with chemical rockets. You'd need something more efficient. Nuclear fusion might work. Fuse hydrogen into helium. Use the energy to accelerate reaction mass. The exhaust velocity could be 10% of light speed or higher. But we haven't built a working fusion rocket. We've barely achieved net energy gain from fusion reactions in laboratory conditions. Building a rocket engine based on fusion is decades away at minimum. Antimatter rockets are even more theoretical. Matter-antimatter annihilation converts mass directly to energy with perfect efficiency. The energy density is unmatched. But producing antimatter is extremely difficult and expensive. We've made tiny amounts in particle accelerators. Nowhere near enough to fuel a rocket. The cost to produce the antimatter for an interstellar mission would be astronomical. Probably more than the entire global economy. Laser-pushed light sails are another idea. Build a large, ultra-light sail. Shine powerful lasers from Earth to push the sail, accelerating it to high speed. This avoids carrying fuel. The energy comes from the laser installation, which stays behind. Calculations suggest that with a large enough laser array and a light enough sail, you could accelerate a small probe to 10 or 20% of light speed. But the laser array would have to be enormous. Hundreds of gigawatts of power. Laser systems miles across. The sail would have to be huge and incredibly thin. Maybe miles across, but mere grams in mass. It's technically possible, maybe. But it's a massive engineering project. And it only works for unmanned probes. You can't put people on a gossamer-thin sail. They need life support, shielding, supplies. That adds mass. More mass means you can't accelerate as fast. The trip takes longer. Or you need more laser power. There's also the problem of stopping. A laser from Earth can push you to speed. But how do you slow down at the destination? There's no laser at Proxima Centauri to push against you. You'd need to carry fuel to decelerate, which adds mass, which makes acceleration harder. Or you accept a flyby mission. Race past the target star at high speed. Take measurements as you go by. Then continue into the void, never stopping. For an unmanned probe, that might be acceptable. For a crewed mission, it's not. You can't send people on a 40-year journey just to fly past their destination. They need to stop, explore, establish a presence. That requires propulsion for deceleration. Which brings us back to the mass problem. The bottom line is that interstellar travel with humans is not feasible with current technology. Not even close. It might become feasible in the future, with fusion or antimatter propulsion, with better life support that can sustain people for decades, with solutions to the radiation problem, with spacecraft that can function reliably for the entire journey. But we're talking about technology that doesn't exist and might not exist for centuries. And even if we solve the propulsion problem, the environment of interstellar space itself is brutally hostile. Far from any star. No sunlight. No heat. The cosmic microwave background is the only external radiation at about -454 degrees Fahrenheit or -270 degrees Celsius. A spacecraft in interstellar space would have to generate all its own power. Nuclear reactors, probably. Radioisotope thermoelectric generators, using the decay heat of plutonium or similar elements. These provide power for decades. Voyager 1 and 2 use them and still function after 45 years. But they produce only hundreds of watts. Enough for instruments and communication. Not enough for life support for humans. You'd need much larger reactors. Megawatts of power. Enough to run life support, recycling, habitat heating, all the systems needed to keep people alive for decades. Launching that much radioactive fuel is a challenge. Safety concerns if the launch fails. Political concerns about nuclear material in space. And reactors degrade over time. Can you build one that runs reliably for 40 years or more, with minimal maintenance? In the zero-gravity, extreme temperature environment of deep space? Maybe. But it's not proven. Radiation in interstellar space is also a concern. No nearby star means no solar wind to deflect some of the galactic cosmic rays. You're exposed to the full flux. A crewed interstellar spacecraft would need heavy shielding, meters of water or other materials surrounding the crew habitat. That's enormous mass. Hard to accelerate to high speed. Or you accept that the crew will accumulate massive radiation doses, greatly increased cancer risk, possible radiation sickness, shortened lifespans. Not a great outcome for a mission that's supposed to establish humanity among the stars. Then there's the time factor. Even at 10% light speed, it's a 40-year journey to Proxima Centauri. Most of a human lifetime. The crew that launches won't be the crew that arrives. They'll be old or gone. You'd need a multi-generational mission. People living and reproducing on the spacecraft. Children born in space, living their entire lives in transit, eventually having children of their own. This generation ship concept has been explored in science fiction. But the reality is staggering. Maintaining a closed ecosystem for that long, preventing inbreeding with a limited population, maintaining social cohesion and purpose across generations. The original crew signed up for the mission. They chose this. But their children didn't choose to be born on a spacecraft. Their grandchildren didn't choose it. How do you maintain morale and cooperation when people have no option but to continue a mission they didn't volunteer for? What if they decide they don't want to continue? What if they want to turn back? By the time they're 20 years into the journey, turning back means another 20 years to get home. It's not really an option. They're committed, whether they like it or not. That's a troubling ethical situation. It raises questions about autonomy, consent, the rights of people born into circumstances they can't escape. Philosophers and ethicists have debated this. Is it right to start a multi-generational mission knowing that future generations will have no choice but to continue it? Or is it acceptable because it's for the greater good of establishing humanity on other worlds? There's no clear answer. But it's a question that would have to be addressed before any such mission could be undertaken, assuming we ever develop the technology to make it possible. Long before that, various catastrophes could make Earth uninhabitable. Asteroid impacts, supervolcano eruptions, climate change, nuclear war, engineered pandemics. Lots of ways civilization could be severely damaged or destroyed. Having humans living in multiple locations, on different worlds, in different solar systems, that provides resilience. If something happens to Earth, humanity could continue elsewhere. This is a long-term perspective, thinking in terms of centuries or millennia. But it's a perspective that makes sense when you consider that our species has been around for a few 100,000 years and could potentially continue for millions of years if we don't destroy ourselves. From that viewpoint, learning to live in space, developing the technology to survive in hostile environments, establishing permanent settlements beyond Earth, these become important long-term goals. But we're nowhere near achieving this yet. The challenges are immense. Deep space is fundamentally hostile to life as we know it. Life evolved on Earth under specific conditions. Pressure, temperature, radiation levels, gravity, all the parameters that define our environment. We're adapted to these conditions. Our biology assumes they'll continue. Take them away, and we don't function. Simple as that. We can create artificial environments that mimic Earth's conditions. That's what spacecraft and spacesuits do. But these artificial environments are fragile, dependent on technology that can fail. The natural state of the universe is hostile to us. The tiny bubble around Earth, where we can survive naturally, that's the exception, not the rule. Most of the universe is vacuum, radiation, extreme temperatures, places where complex life simply cannot exist. There might be other places where life has evolved. Other planets around other stars with their own protective atmospheres and magnetic fields. But these would be rare, scattered islands in a vast ocean of hostility. And the distances between them are measured in light years. Even if there are habitable worlds around nearby stars, reaching them with current technology would take tens of thousands of years. Multiple generations born and passing in transit. A ship that functions as a self-contained biosphere for that entire time. The engineering challenges are beyond anything we can currently achieve. So for now, for the foreseeable future, deep space remains a place we can visit briefly with extensive support, but not a place we can live without constant technological intervention. It's worth understanding this, really understanding it, because it gives perspective on how remarkable Earth is. This planet is our home, not just in a sentimental sense, but in a literal biological sense. We are made for this place. Our bodies, our chemistry, our every cell assumes Earth's conditions. We fit here in a way we don't fit anywhere else in the known universe. That makes Earth precious, irreplaceable. The only place in the cosmos we know for certain can support human life naturally. We should take care of it, because the alternative, living permanently in space or on other worlds, is far harder than most people realize. It's not impossible. Technology improves. We learn more. We develop better solutions. But it's going to require solving enormous challenges. Creating closed-loop life support systems that can function for decades without resupply. Developing radiation shielding that actually works against cosmic rays without being impossibly heavy. Building habitats that can maintain Earth-like conditions reliably for years or centuries. Solving the medical problems of long duration, spaceflight, bone loss, muscle atrophy, radiation damage, psychological stress. Creating sustainable food production in space. Recycling everything. Air, water, waste. Because you can't just throw things away. Developing propulsion systems that can reach other worlds in months instead of years. Eventually, maybe faster than light travel, though that might be physically impossible. All of this is science and engineering on a scale humanity has never attempted. Some of it might be achievable in the next century. Some of it might take longer. Some of it might be fundamentally impossible with any technology. We don't know yet. But what we do know, what the physics tells us clearly, is that deep space is hostile. Vacuum, radiation, temperature extremes. These aren't problems that can be solved with willpower or optimism. They're fundamental challenges rooted in the laws of physics. You can't negotiate with vacuum. You can't reason with radiation. You either have the technology to protect against these things, or you don't. And if you don't, exposure to deep space is rapidly fatal. No one survives it. Not for more than a minute or two at most. The movies lie. The stories lie. They have to, because the reality is too harsh for drama. Heroes don't float peacefully through space. They don't slowly freeze with time for final words. They experience rapid, violent, physiological failure, consciousness lost within seconds, brain death within minutes. It's not dramatic. It's just physics. This isn't meant to be depressing. It's meant to be realistic. Space is beautiful, awe-inspiring, worthy of exploration and study. The images from telescopes, the discoveries about distant worlds and galaxies, the physics and chemistry of the cosmos, all of this is profoundly interesting. But space is also dangerous in ways that are hard to overstate. It's an environment fundamentally incompatible with human life. Understanding this, really grasping what it means, that gives us appropriate respect for the challenge. It helps us appreciate what astronauts do when they venture beyond Earth's protection. They're not just brave. They're trusting their lives to engineering, to spacecraft and spacesuits, to life support systems that have to work perfectly, or the consequences are immediate and fatal. Every spacewalk, every mission, that's people putting themselves in an environment where a single failure could end them in seconds. They do it anyway because they believe it's worth the risk. Because exploration matters. Because pushing boundaries, learning new things, extending human presence beyond our home world, these are endeavors worth pursuing even with significant danger. But it's important to remember it is dangerous. Genuinely, seriously dangerous. Not in an abstract way. In an immediate, physical, this can end you in seconds way. Deep space doesn't care about your courage or your dreams or your mission. It's an environment governed by physics. Pressure, temperature, radiation. These things operate according to laws that don't bend for human needs. You either protect against them or you suffer the consequences. So when you hear about plans for missions to Mars, to the outer solar system, to other stars eventually, remember what's actually involved. It's not like the movies. It's not a casual adventure. It's people volunteering to spend months or years in a tiny artificial environment, completely dependent on technology, knowing that any major failure could be fatal and there's no quick rescue. It requires extraordinary engineering to make it possible, extraordinary courage to undertake it. And even then, even with the best preparation, the best technology, the best people, there's risk that can't be eliminated. Space is hostile. Deep space is hostile in ways that test the limits of our ability to protect against. And true interstellar space, the void between stars, that's even worse. No star nearby means no light, no heat, just the cosmic microwave background at a few degrees above absolute zero. Radiation from cosmic rays with no nearby star to provide any shielding effect. Distances so vast that communication with Earth would take years or decades. A spacecraft in interstellar space would be truly alone, months or years from the nearest star, light years from home. If anything went wrong, there would be no help, no rescue mission. The crew would have to solve problems themselves, or they wouldn't survive. This is the reality of deep space. It's hostile, unforgiving, and utterly indifferent to human survival. We can venture into it, but only with massive technological support. And even then, only briefly and at great risk. The notion of humans living routinely in deep space, traveling casually between stars, settling distant worlds, that's science fiction for now. It might become science fact eventually, but it's going to require solving challenges that we're only beginning to understand. For now, Earth is our home. The only place in the universe we can survive naturally. A thin shell of atmosphere, a protective magnetic field, a stable temperature range, liquid water, an oxygen-rich atmosphere. All of this is rare, probably very rare, in the cosmos. And it's all we have. Understanding what deep space is really like, understanding how hostile it is, that gives perspective. It makes us appreciate this planet more. It makes us take seriously the need to protect Earth's environment, to preserve the conditions that allow us to live here. Because the alternative, surviving in space without Earth's natural protection, is far harder than most people imagine. So, the next time you look up at the stars, remember what's really out there. Not just beauty and mystery and endless possibilities, but also vacuum, radiation, temperature extremes. An environment that would end you in less than 2 minutes if you were exposed to it directly. Space is magnificent, but it's also merciless. And that's the real reason. No one can survive deep space without extraordinary protection. It's not a failure of courage or technology, though technology is limited. It's just physics, the fundamental nature of the universe. And physics doesn't negotiate. Thank you for joining me on this journey through the harsh realities of space. If you found this exploration valuable, a like or subscribe helps us continue making these deep examinations of the cosmos. And remember, Earth is special. A rare oasis in a hostile universe. The only home humanity has ever known. The only place we can survive without constant technological support. That makes it worth protecting, worth cherishing, worth understanding in all its fragile, precious, irreplaceable glory. Good night, and may you never take for granted the thin shell of atmosphere that keeps you alive.